GIS Fundamentals, Section 15, New Developments in GIS. GNSS. Three trends will dominate GNSS innovation over the next decade: multi-GNSS receivers, miniaturization, and system integration. Dual GPS GLONASS systems already exist, and systems that simultaneously support the Galileo and Chinese compass system will be developed, further increasing accuracy, availability, and reliability. Receivers will commonly have hundreds of channels and track tens of satellites even when under heavy forest canopies, in canyons, and among tall buildings, bringing real-time, precise positioning to everyone. GNSS receivers will cost less, shrink in size and weight, and increase accuracy for some time to come. And these improvements will spur even more widespread adoption of this technology. A few years ago, it was uneconomical to track objects smaller than a cargo ship. Now, trucks or containers are routinely followed. In the near future, it may be common to track individual packages. Ubiquitous, inexpensive, or free differential correction signals are substantially improving the accuracy commonly achieved with GNSS. Virtual Reference Station, or VRS networks, promise to allow sub-meter, even near centimeter level positioning in real time. Fixed and mobile three-dimensional mapping. GNSS is also being combined with new advances in ground-based laser scanning to increase the scope, accuracy, and efficiency of spatial data collection. Three-dimensional scanning devices have been developed that measure the horizontal and vertical location of features. The GNSS is used to determine the location of the scanning laser. The horizontal and vertical offsets from the scan point are measured by the laser. These measurements are combined with coordinate geometry to calculate the precise positions for all features scanned in the field. The trend of multi-technology integration will accelerate for rapid centimeter-level mobile mapping. One can imagine self-driving automobiles that navigate via a combined GNSS, LiDAR, GIS, using systems to avoid collisions via real-time distance measurements and wireless communications with nearby automobiles. Efforts will move from a focus on development of integrated turnkey data collection systems to software and methods that automate workflow, so that data may travel from the device to the database with as little human intervention as possible. Highly accurate, current data may spur the adoption of heads-up displays, HUD, in automobiles. Data modernization. New datum realizations will be calculated based on improved measurements. Datum shifts among ITRF-based datums will remain small, but planned datum adjustments for the NAD83 datums over the next decade may result in quite large shifts. These shifts will be for the most part due to changes in the way the datums are calculated, and only slightly due to improved measurements. There are large differences between the NAD83 family of datums used primarily in North America. and the ITRF datums used by most of the rest of the world. The ITRF is an Earth-centered system based on measurements of the X, Y, and Z locations and velocities of points. It places the origin of the adopted ellipsoid at the best estimate of center of mass of the Earth at the time of each adjustment. The post-1986 NAD83 datums are also Earth-centered. In contrast to the ITRF system, the NAD83 datums have not adopted the best measurements of the Earth's center, but rather a position compatible with older NAD83 datums. Improved remote sensing. Spatial data collection will be substantially improved with the continuing advances in remote sensing. More satellites, higher spatial and temporal resolution, improved digital cameras, and new sensor platforms will all increase the array of available data. The Worldview system. 3 satellites have been launched, the latest with a 0.25 meter spatial resolution. Aerial cameras increase in spatial resolution, meaning increasing availability of detailed images, with higher radiometric sensitivity, yielding a broader range of applications. LiDAR systems are increasing in accuracy and resolution and declining in cost, with coordinate data commonly paired with digital aerial images. LiDAR data are dropping in cost, and county to statewide LiDAR mapping will likely become common. Data development, management, analysis, and visualization is currently taking place across architecture, CAD, surveying, and GIS softwares and disciplines, and substantial development and fusing across these disciplines is in the offering. Advances in full-sized and miniature aircraft, known as drones, remotely piloted vehicles, or unmanned aerial vehicles, are leading to increased availability of a broader range of aerial imagery. Remote sensing is also venturing indoors, enabling data collection of building interiors. Cloud-based GIS. Cloud-based GIS provides data storage, analysis, and display capabilities over the Internet, with services usually provided from one or multiple remote locations via the Internet. Economies of scale in data storage and maintenance, or in computing power, may be favorable, as well as the centralization of specialized technical support. Additional capacity may be added as needed, as market share grows, or specific project demands increase. Resources may be scaled up or back as needed. New capabilities may be rented or tested more easily, and software functions may better adopt a rental model and pricing structure. Cloud computing may also provide faster, broader, safer, and more continuous data access. Internet connections are increasing in speed, and solid-state memory in large installations provides faster access yet. Large server arrays may be outfitted with proper backup and protection, including data mirroring at distant locations. Mirroring provides data redundancy because the same data are stored concurrently at different physical facilities, often miles or even countries apart. Internet mapping applications are particularly appropriate when a large number of users need to access a limited number of data layers to compose maps. Most internet mapping applications are built for users who have little knowledge of spatial data, maps, and analysis. The suite of spatial operations allowed is usually very sparse. Most internet mapping is currently limited to creating simple displays. One major limitation of the cloud model is its dependence on a fast connection to the cloud of resources. Slow internet speeds become a hindrance, particularly with large data or image sets that characterize many spatial analysis. Each zoom, pan, or layer addition may require a scene to be repainted, involving the movement of billions of pixels through the web connection. Widespread, fast internet should be forthcoming, but access may depend on internet demand as well as supply. OpenGIS. Open standards for GIS. The development of open standards in computing is driven by the notion that the larger user community benefits when there are no technical barriers that inhibit the free exchange of data and methods. Open standards seek to establish a common framework for representing, manipulating, and sharing data. Standards have been developed in a number of endeavors. For example, the ISO 9600 specifications for physical storage formats allow any manufacturer, data developer, or user to build, read, write, or share data on hard drives, optical disks, tapes, or other storage devices. Open standards for spatial data are the responsibility of the OpenGIS Consortium. The OpenGIS Consortium has developed a framework to ensure interoperability. They do this by defining a general common set of base data models, types, domains, and structures, a set of services needed to share spatial data, and specifications to ease translation among different representations that are compatible with the OpenGIS standards. Data developed by a civil engineer and stored in a raster format on a Unix version of ArcInfo should be readily accessible to a soil scientist using GRASS on an OS X Apple system. Open Source GIS. The open source organization requires that the software is not only by design restricted to a specific operating system or other technology, that there can be no royalties, and that there be no explicit discrimination against fields of endeavor, persons, or groups. But the main defining characteristic of open source software is an open, grassroots network of collaborators developing, documenting, and freely sharing source code. Open source use is a large, growing phenomenon for many reasons. High software costs are driving many organizations toward open source software. Licenses for some commercial products are tens to hundreds of thousands of dollars annually for some large organizations. If these organizations employ staff programmers, open source GIS may meet geoprocessing needs at a reduced cost. Many organizations use open source GIS because commercial products may not provide the required functions or capabilities. China, India, and Brazil have all supported open source software in general, and operating systems in particular, to maintain independence from foreign films, reduce costs to government and local business, and develop local information technology expertise. Because these nations are home to more than a third of the world's population, their actions alone are substantially increasing the use of open source GIS. A hybrid model. Proprietary software vendors may adopt a hybrid software approach, where they interact with open software and systems. GIS Fundamentals, Section 15, New Developments in GIS, Section Summary. GIS are a dynamic collection of conceptual models, tools, and methods that use spatial data. As such, they will continue to evolve. What becomes standard practice in the future may be quite different from the methods we apply today. However, the fundamental set of knowledge will remain unchanged. We will still gather spatial and attribute data, adopt a spatial data model to conceptualize real-world entities, and use map coordinates to define positions in space. The coordinates are likely to remain based on a standard set of map projections, and we will combine the spatial data of various classes of entities to solve spatial problems.